And with that, good morning everybody. Welcome back to Calc 1. Plan for today is, as promised, I have a quiz for you on Standard 18, and then we're going to jump into Standard 19, the last standard of the semester. Really? Indeed. A couple things. One, you can't tell from my voice or the intermittent coughing, I got sick this weekend, which I'm feeling a lot better today. I have to teach at least, but I didn't get any grading done over the weekend, so I didn't grade last week's quizzes or any retest. I apologize for that. I'll try and get those quick graded by, as well as these quizzes graded by tomorrow. As far as office hours go, yeah, kind of completely revamped my office hours for the next couple days for a variety of reasons. Today I have to cancel my morning office hours, so today I'm only going to have office hours today from 1 to 2. And tomorrow, I have to, changing my afternoon office hours to morning office hours, so I've got office hours tomorrow morning from 10 to 11:30. So hopefully that works out for you. If you wanted to retest and you can't make either of those times, send me an email to let me know and see if we can work something out. I'm not assigning you homework. Have a good Thanksgiving break. Any questions or comments before we get started for today? Why was algebra so easy for the Romans? It's because whenever they needed to solve for x, they always got x equals 10. Roman numeral joke. Consecutive Roman numeral joke days. And with that, it is quiz time. Quiz is out. Quiet in the room, please. go ahead and take a few seconds to finish up your thoughts. And pass your quizzes in, please.
Oh, I always forget to put my name.
Thank you, James, for saving me for some confusion. Alrighty. So, here's the game plan for today. Standard 18, we talked a lot about how can you approximate the area under a curve using like some finite amount of rectangles. So for instance, if we want to define the area under f of x equals x squared from 1 to 5, we said last time we said, well, you can use a left or right endpoint approximation. And standard 18, we're able to show that the actual area has to be somewhere in between 30 and 54. And what I want to do today, I want to find the actual area under this curve. Meaning I want to find the exact number, not just an approximation. Something that engineer Morgan back there can be proud of. So we said in general, the number of rectangles that, as you use more rectangles, the approximations are generally going to become more and more accurate to what the actual area should be. And we said explicitly, and we said in passing that if you take a limit as n goes to infinity of r sub n, or of L sub n for that matter, that as the number of rectangles you use goes to infinity, you get less and less over-underhang from your rectangles in the curve, and the area approximation you'll get will get closer and closer to the actual area. So this is going to be our goal for today. It's going to be compute this expression. And that is going to be the goal of standard 19, which is going to be on the fundamental theorem of calculus. Oh, before I do that, something I forgot to mention last Friday. If any of you are interested in signing up for my morning section of Calc 2 next semester and didn't get in because it filled up, send me an email to let me know. I've got a wait list going for the class, and if you're not already in, I might be able to squeeze you in. Just send me an email as soon as you can, and I'll put you on my wait list for the class. All right, before we start going into area approximations, I have a story I want to tell you. Story about a mathematician named Carl Friedrich Gauss. So, Gauss was a German mathematician, did did most of his work in the 1800s. Famous. He's probably one of the top 5, I would argue, most famous mathematicians of all time, because he kind of did everything in math. You name a branch of math, he probably did some influential work in it. He had his fingers in a lot of mathematical and also physics pies, in other words. But I want to tell you about today, the story of Gauss's childhood. When he was in the 19th, I think this is 1700s, 1700 German equivalent of grade school. Where apparently, as legend has it, Gauss was a bit of a show-off. And he's really good in class, loved showing up the teacher. And so the teacher got fed up with this one day and tried to assign Gauss a task that would keep Gauss out of his hair for a while. And all right, Gauss, I want you to add up for me all the positive integers, 1 plus 2 plus 3, all the way up to 100. Thinking, that'll keep Gauss out of my hair for a little while. He won't be able to add those up. Even that many numbers. Even Gauss wouldn't be able to add that many numbers up that quickly. As legend has it, Gauss figured out a way to add these all up in about 30 seconds. He had a trick. Here's what Gauss's trick was. He took the numbers from 1 to 100 and wrote them out in 2 columns. First column had all the numbers going down from 1 to 50. Second column, he had all the numbers from 51 to 100, except going upwards. And what Gauss's idea is instead of just adding 1 plus 2 plus 3 plus 50 plus 51, blah, 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 let's add across rows and then add up the sum of each row instead. So, Emery, what do we get if we add 1 to 100? What do we get if we add 2 to 99? What do we get if we add 3 to 98? What do we get if we add 50 to 51? Gadzooks. So, what Gauss did was he noticed that, hey, if you kind of line these numbers up correctly and start adding them together in pairs, if you add smallest to biggest and then second smallest to second biggest and so on, you get 101 each time. So in essence, adding up all the numbers from 1 to 100 is the same as adding up 101 to itself with 50 copies of 101. And if we were to add 101 to itself 50 times, what's an easier way to do that than taking 101 plus 101 plus 101 plus 101 plus 101? Man, Disney would have a field day with this. They're Dalmatians. What's a quicker way to do this than literally taking 50 different sums? James?
101 times 50.
Yeah. If you're just adding the same number to itself 50 times, that's the same as taking 50 copies of 101. Or you could just take 101 times 50, which 100 times 50 is 5,000, 1 times 50 is 50. Boom, there's your answer. The sum of all numbers from 1 to 100 is 5,050. So apparently Gauss figured this out when he was like 10 in like 30 seconds. And I don't know how a mere mortal's supposed to figure out a trick like this, but that's why he's one of the most influential mathematicians of all time, I guess. Go figure. But this process has been called Gauss's trick for adding up sums. Any questions or comments about what went on here? So it turns out you can generalize this process without too much hassle. and that if you want to ever add up all the numbers from 1 to some n, you can basically repeat the instead of 100 specifically, if you want to find a general formula for what happens when you add up all the numbers from 1 to n, well, you could basically do the same trick. In which, if you kind of add across each row like this, you're going to get n plus 1, n plus 1, n plus 1, n plus 1. And so, if in other words, if you wanted to add up all the numbers from 1 to an arbitrary n, that's the same as adding n plus 1 to itself, n divided by 2 times. Where the reason why you have n over 2 copies is the same reason we had 50 copies there, because you have 1 copy for each number from 1, 2, 3, all the way up to n over 2. So what that's going to tell us is that the sum from 1 plus 2 plus 3 all the way up to n, doesn't matter what your n is, it's always going to be equal to n plus 1 times n over 2, or as it's usually written, n times n plus 1 all over 2. And yes, technically this only works if n is even. If n is odd, you have to make a slight tweak to this chart, but it comes out to the same answer either way. You can also, if you want to get even cheekier, come up with a formula for 1 squared plus 2 squared plus 3 squared all the way up to n squared using a sort of similar technique, which is going to give you n times n plus 1 times 2n plus 1 all over 6. And if you wanted to add, say, 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed, turns out you'll just get n times n plus 1 over 2 quantity squared. So this sort of, if you want a little math parlor trick you can use to show off to your family over Thanksgiving, try using one of these formulas. Say like, I can add up all the numbers from 1 to 1,000 in just in less than a minute. Just take 1,000 times 1,001 over 2. Not the easiest thing in the world to compute, but a heck of a lot easier than trying to literally add 1 plus 2 plus 3 plus 4, that plus 1,000. And so these are going to be formulas that we're going to need to help us out along the way in Standard 19. Any questions or comments about these formulas? Alrighty, in that case, moving on to the second page of the packet now. It's time we define ourselves the second type of integral. You know how early on we've been, instead of just calling it an integral, sometimes I've been calling it an indefinite integral, the process of finding antiderivatives. Well, now it's time for integral type number 2, the definite integral, where we're going to define the definite integral integral from a to b of little f of x dx is going to be the area underneath the graph of f of x from x equals 1, or not x equals 1. it's going to be x equals 1 in the example we do, from x equals a to x equals b. So this expression right here, this definite integral, it's very unlike the indefinite integral, where when you want to look for what's the indefinite integral of a function, you're looking for the family of all the antiderivatives. So when you look at indefinite integral, your answer should always be a bunch of a whole family of functions getting together to celebrate. I'm in the Thanksgiving spirit, as you can see. But when you talk about the definite integral, the answer is going to be an area, which means when you take a definite integral, your answer should be a number. Not a family of functions, but a single number, corresponding to what is the area under the curve. So with that in mind, let's go ahead and find what the actual area is underneath the graph of f of x equals x squared from 1 to 5. And the way you know you have a definite integral as opposed to an indefinite integral is with a definite integral you've got little numbers alongside your integral symbol, telling you from left to right what's kind of the region of x values you're looking for, the area under the function over those x values. So in this case, if we write it out like this, integral from 1 to 5 of x squared, what that's going to tell us is the area underneath the graph of f of x equals x squared from x equals 1 to x equals 5. All right. Y'all ready for this? I'm excited. This is going to get fun. So what I'm going to choose to do is to find the actual area. I'm going to take an arbitrary r sub n and then take a limit as n goes to infinity. So let's take a look at this graph. If we have n rectangles, yes, I know you could say n equals 5 in this graph, but bear with me. Pretend like you can't count that high. How would we find the width of each of our rectangles if all that we know is we have n of them? Here's it. Anna, any ideas?
Could you find out how many, do n, well, can you not count them, looking at the graph?
In this specific example you can, but I want a general expression because what we're going to be doing is we're not going to be looking at a single r sub n. We're going to say, in this case, the way I drew it out, it has 5, but I just drew it out that way to help illustrate the point I'll make here in a minute. We can't necessarily say the width is always going to be 5 if n is changing. So what I would like to have is an expression that's in terms of n somehow for the width of a single rectangle. Morgan?
We do 5 minus 1 over n.
Okay, so do length of the interval divided by number of rectangles?
Yeah.
Yeah, absolutely. We do the same thing we've been doing all along. Take the length of your interval, divide by number of rectangles. And so we'll end up here with the width, I would say, 5 minus 1 over n, or 4 over n. Where if we're using n rectangles, the width is going to be 4 over n. So you could say, for instance, if we have 2 rectangles, the width will be 4 over 2, or 2. If we have 8 rectangles, their width is going to have to be 4 over 8, or a half. If we're using a billion rectangles, then their width is going to be 4 divided by a billion. So that when we add up the widths of each rectangle, it adds up to the length of the interval, which in this case is going to be 4. Okay, so here's a question. That tells us how to find the width of each rectangle, but finding the height is going to be a little bit slow. So let's say we know, for instance, that each of our rectangles has a width of 4 over n. So you have to go 4 over n to get from here to here. Get from here to here. We're going to have a width of 4 over n. Here to here. Going to have a width of 4 over n. And so on. As an expression in terms of n, if we want to find the height of our first rectangle, we need to know the x-coordinate of where this first rectangle ends. What's the x-coordinate of this point right here? Aiden?
1 plus 4 over n.
1 plus 4 over n. I like it. Yeah, because we know to get from x equals 0 to here, that has a length of 1. To get from here to here, you go out 4 over n more. So to get from x equals 0 all the way to this point, that's going to have a width, or that's going to have a x-coordinate of 1 plus 4 over n. So if we want to find what's the area of our first rectangle, well, we're going to take width times height. The width is 4 over n. The height is going to be, well, what we get when we plug 1 plus 4 over n into our function. Because the height of this rectangle, if we're doing an r sub n, is just going to be, you take your right endpoint of the first rectangle, 1 plus 4 over n, plug it into the function to get the height of that rectangle. How about our second rectangle? So for the second rectangle, we need to know the x-coordinate of this point. So how can we find the x-coordinate of this, the right endpoint of the second rectangle? Doing something similar. Emery?
1 plus 2 times 4n.
1 plus 2 times
4 over n.
4 over n?
Yeah.
How'd you get that?
Well, it's the interval you have to go to is twice what you have to go to first with the 4 over n.
Yeah, so we know we can travel out 1 to get to where the first rectangle starts. To get to where the second rectangle ends, we're going to go 1 and then 4 over n and then 4 over n again, which is going to give us 1 plus 8 over n. So our second rectangle is going to have an area of 4 over n times f of 1 plus 8 over n this time. Where 4 over n is still going to be the width of each one of our rectangles. Then our second rectangle has a right endpoint of 1 plus 8 over n. So we need to plug that into our function f to tell us what the height of the second rectangle is going to be for doing a right endpoint approximation. We could keep going if we wanted to. The next rectangle is going to be 4 over n times f of 1 plus 12 over n. If we go out another 4 over n. And then each time we go from one rectangle to the next, we're going to keep adding 4 over n to get to the previous rectangle's endpoint to get the next rectangle's endpoint. So the next one will be 1 plus 12 over n, 1 plus 16 over n, and so on. How about our last rectangle? Well, it's going to have a width of 4 over n. How do we find the height of our final rectangle? Yeah.
Is it just 4 times 5?
I don't think it's going to be 4 times 5, but I think you're close. Morgan?
So 4 over n times of 5 minus 4 over n?
4 over n plus 5 minus 4 over n. So it sounds to me like you're just
I'm
saying,
saying the height is 5 minus 4.
well, the height is going to be, we have to plug something into our function f.
Yeah, that's what I'm saying.
Here's how I would think about it. We have n rectangles. Each time we go from one rectangle to the next, we're going to be adding you have to take one to start, and then each time we go to a new rectangle, we have to add an additional copy of 4 over n. So what I think we want to do is we want to take, we're running out of space here, 1 plus 4 over n copies of 4 over n. So it's going to be 1 plus f of 1 plus n times 4 over n.
Would be just cancel out, be 1 plus 4.
It would indeed. Turns out if we simplify this, surprise, it ends up just being f of 5, which I hope makes sense because we know our last rectangle should end at 5, kind of the right endpoint of the interval we're looking at. So we know what the height it should come out to just be f of 5 here in our graph. But the way I'm going to write this is I'm going to write this as f of 1 plus 4n divided by n. And the reason why I write it that way instead of writing out 5, I hope will become clear in the next couple of lines. All right, we have ourselves an algebraic mess here. Well, first of all, first of all, how do we find f of 1 plus 4 over n? What does it mean to find f of the quantity 1 plus 4 over n here? John?
You can plug 4 over n into the original equation,
What's our original function?
6 squared.
Yeah. When we take f of thing, since our f of x is x squared, at least for this particular example, what we would do is we would take 1 plus 4 over n quantity squared. We're just taking the 1 plus 4 over n, plugging it into our function f of x. And similarly, we'll take 4 over n times 1 plus 8 over n quantity squared, plus a whole lot of plus 4 over n times 1 plus 4n over n quantity squared. So, all right, well, let's square each of our terms to see what we get. I'm going to go ahead and, since each of these terms has a factor of 4 over n, I'm going to pull a 4 out of n in front of the whole expression. Just kind of factor a 4 over n out, since we have 4 over n times thing, plus 4 over n times thing, plus 4 over n times thing. I can go ahead and just pull a copy of 4 over n out in front. And what we'll be left with, well, when we evaluate that, we'll get 1 plus 8 over n plus 16 over n squared. This one will be 1 plus 8 times 2 is 16 over n plus 64 over n squared. Here we'll get 1 plus, 8n over n plus 16 n squared over n squared. Which, if we keep going, where does the madness end? I'm going to regroup all of these terms. I'm going to combine the ones together. The blip over n terms together, and the blip over n squared terms together. So we're going to get 1 plus 1 plus 1, where we'll have n copies of adding 1 together, plus 8 over n plus 16 over n plus plus 8n over n, plus 16 over n squared plus 64 over n squared plus 16 n squared over n squared. Y'all having fun yet? So much. Alright, I'm out of board space. I'm gonna move over here. Move over there. Let's move over. I need more board space. Let's move over here. Well, we still have a limit as n goes to infinity of 4 over n times stuff. Question. If we had 1 plus 1 plus 1 over and over and over, n copies of 1 that we're adding together, what is that going to come out to? If I were to give you n copies of the number 1 and ask you to add them together. John Henry?
Just end, right?
Yeah, it'd just be n. If I gave you like 3 copies of 1, asked you 1 plus 1 plus 1, well, that just comes out to 3, the number of copies of 1 that you're adding together. Same in general for n. So this expression is going to come out to be equal to plain old n. This expression looks ugly. Unless we factor out an 8 over n from that expression. Because if we factor out an 8 over n, what is this expression going to be? 1 plus 2 plus 3, all the way up to plus n. And if we factored out, say, a 16 over n squared from this final expression, what are we going to get? We're going to get 16 over n squared times 1 squared plus 2 squared, all the way up to n squared. And now, I put it to you, Morgan. If I were to take 1 plus 2 plus 3 all the way up to n, how can we simplify that?
By using like the n times n plus 1 over 2.
Yeah, we can use one of Gauss's formulas, the n times n plus 1 over 2 expression. And, let's see. Emerson, how about the 1 squared plus 2 squared all the way up to n squared?
We can use the other trick, which was n times n plus 1 times 2n plus 1 over 6.
Good golly. We can indeed. And suddenly, our giant algebraic mess has become, using Gauss's tricks, a somewhat smaller algebraic mess. All right. So, let's see. So we're going to have a limit as n goes to infinity of 4 over n times n plus 8 over n times n plus 1 over 2 plus 16 over n squared times n plus 1 times 2n plus 1 all over 6. And you don't need to write this line down again. I'm just kind of copying this over from over here, that last line. Well, let's see if we can simplify this a bit. N times n plus 1 over 2, I think is going to be n squared plus n over 2. This is going to give us n squared plus n times 2n plus 1 over 6, which is going to be 2n cubed plus 2n squared plus 3n squared plus n all over 6. Which now I'm gonna multiply the 8 over n through, and we're gonna get some fractions. We're gonna get n plus 8n squared plus 8n all over 2n plus 32n cubed plus 48n squared plus 16n all over 6n squared. And then, just because I'm a nice guy, I'm going to multiply the 4 over n through, distribute that through to each one of these terms. And what that's going to give us is 4n over n plus 32n squared plus 32n over 2n squared plus, 32 times 4 is 128 n cubed plus 96, 192 n squared plus 64n all over 6n cubed. Y'all doing okay? Franklin's not? That's okay. Alright, Franklin, I'll ask you this. As n goes to infinity, what's going to happen to 4n over n? Yeah, doesn't matter what n is. Well, as long as n is non-zero, 4n over 4 is always going to be equal to 4. So, if we take a limit as n goes to infinity of each one of these terms, the first limit as n goes to infinity of 4n over n, is just going to be 4. How about this next limit? Limit as n goes to infinity of 32n squared plus 32n all over 2n squared. I've got a trick for you. If you're ever taking a limit as n goes to infinity of polynomial over polynomial, all you need to look at is the highest powers of n that show up in your numerator and denominator and compare those. So James, if we were to take a limit as n goes to infinity of 32n squared over 2n squared, what would we get?
16n squared. Or no, just 16.
The same. The n squareds would cancel out and we'd just be getting a limit of 16. Just like we got 4 over n there. And Caleb, how about if we took a limit as n goes to infinity, just using our highest powers of n here, 128n cubed over 6n cubed.
128 over 6.
Plus 128 over 6. And just like that, our n's are all gone, and we are left with a number. Let's see, that's going to be 20 plus 64 thirds, if we divide top and bottom of this by 2. Which is the same as 20 plus, I think, 21 and a third. And our final answer for the area underneath the graph of f of x equals x squared from x equals 1 to 5, the actual area 41 and a third. and a third fall in the region that we found in standard 18 packet, in the 30 to 54 region. It does. Nora, I think you had suggested last week, could we get an approximation by just taking the average of the left and right bounds, do something like 30 plus 54 all over 2? If we had done that, we would have gotten 42, which is not the exact area, but 42 is pretty close to this number. So that would have given us a pretty good answer. All right. That's standard 19 in a nutshell. When it comes time for the standard 19 quiz, I will give you a function. And it won't be a simple one like n squared. No siree. It'll be something like sine of n cubed all over 5.
But we have the
And you'll be asked to go through the process of setting up this limit, evaluating this sum, and getting the number in the end.
But we have the entire class period.
Usual 10 minutes.
I was gonna ask if you could give us like an extra 5 minutes, but
I'll give you an extra 5 minutes. Oh. Yes, Franklin?
You're kidding, right?
I never kid. Yes, I'm kidding. So now that I've thoroughly, I hope, scared you all, now we'll actually talk about what is standard 19 actually about. So here's the thing. I wanted to scare you with this. This is just finding the area under x squared. I mean, f of x equals x squared is a pretty simple function, relatively speaking, to most of the functions we've been looking at in this class. Can you imagine if I had given you a more complicated function, how messy this would have been? It would have been ridiculous. Turns out, I wanted to scare you straight into thinking, oh no, areas are scary, so that now, when we introduce the new way to find areas, you can ooh and ah at how much simpler it is. And to do that, we're going to need the most important theorem of the semester. Fundamental theorem of calculus. This is the only time you'll ever see me write out fundamental theorem of calculus in full on the board. I'm going to call it FTC from this point forward. What this theorem says is, suppose f of x is continuous on the interval from a to b, and that big F of x is an antiderivative of little f of x. Then if you want to find the area underneath the graph of little f of x from x equals a to x equals b, all you have to do is take big F of b minus big F of a. And that will give you the area underneath the graph of f of x from a to b. So let's look at an example. Or let's do this example. Use fundamental theorem to see if we can get the same answer with a lot less scariness going on. So, Nolan, can you give me an antiderivative of x squared?
1/3 x to the 3rd plus c.
Give me a value for c. I want a specific antiderivative.
5.
Okay. Big F of x equals 1/3 x cubed plus 5. That is an antiderivative of little f of x equals x squared. If we differentiated 1/3 x cubed plus 5, we would just get x squared. So according to the fundamental theorem of calculus, if we want to integrate, if we want to find the area under x squared from x equals 1 to 5, all we have to do is take big F of 5 minus big F of 1. That's it. Well, that's not it. We have to actually evaluate that. But we'll have to take 1/3 times 5 cubed plus 5 minus 1/3 times 1 cubed plus 5, which, oh, we'll go ahead and erase this. Is going to be equal to 5 cubed is 5 times 5 is 25, times 5 is 125. It's going to be 125 thirds plus 5 minus 1/3 minus 5. Carson, what happens to the 5 terms? Swoosh, swoosh. That's just going to give us 124 thirds, which is 41 and a third. Would you look at that? Same answer. Franklin, which of these methods do you prefer, first or second?
The second one.
If you had said first, I was going to force you to do the first method on the quiz.
Oh.
But yeah, this is why the fundamental theorem of calculus is so cool. Normally, to find your area, you would have to, for a long time before the fundamental theorem of calculus was discovered, in order to find the actual area under a curve, you had to set up and do this sort of nasty limit as n goes to infinity of r sub n or L sub n. This process right here, by the way, we call taking a Riemann sum. And what I kind of had wanted to do is kind of illustrate what does a Riemann sum look like to just scare you. But in truth, the sorts of questions I will ask on the standard 19 quiz are something like, find the area under x squared from 1 to 5, in which case you can decide how you want to do it. And what I would highly, highly, highly recommend is that you use the fundamental theorem of calculus. You take an antiderivative, you plug in your right endpoint, you plug in your left endpoint, you subtract, boom, that can give you the exact value for the area under the curve. Yes, Nathan?
Is your right bound always going to be your constant?
Yeah, the right bound and the left bounds are always going to be, in the examples that we do, they will be constants.
Okay.
So basically, because if you want to find area under a curve, you need to find area under a curve between 2 points.
Right. Yes. I mean, in the antiderivative, you're always going to add.
Yeah. So what's up with this plus 5? Well, Nolan gave me the plus 5, but turns out this plus 5 term, Nolan, that you gave me, it didn't matter what constant you gave me. Why did this plus 5 term not matter in the end when we found our antiderivative? Anna?
Because it canceled out.
Yeah, it's because when we took big F of 5 minus big F of 1, as long as we're using the same antiderivative both times, we have a plus 5 and a plus 5 that gets subtracted off. If you would put any plus c for the antiderivative, doesn't matter what the constant was, it would just, you would be adding it and then subtracting it off, and that constant term, whatever it was, wouldn't have mattered either way. So usually for the antiderivative, you would usually just choose the one with the constant term of 0 because it's the least amount of work to write out. But it turns out, since the constant term cancels out, your choice of C in the antiderivative doesn't matter. All right. Really, that's kind of the main points for Standard 19. When we come back after Thanksgiving break, we'll do some more examples of applying the fundamental theorem of calculus. There's a couple quirks that can come out of funny results you can get when you use this theorem. So we'll talk about that Monday after the break. The Riemann sum process, don't worry, I'm not going to ask you a question. I'm never going to make you actually evaluate one of these buggers. I thought it would be good for you to see an example in class, but I'm not going to make you. Fundamental theorem of calculus is where it's at. Have a good Thanksgiving break, everyone. See you all in a week. Take care.